Welcome, calculus students. In this chapter, our first lesson, we're going to be talking about the derivative. And the best way to make use of these notes is to have the printed notes from Shobi in front of you. And these slides that you'll see me writing on are pretty much the same as your printed notes in Shobi. Only at some point in Shobi, you're going to have a problem that will be your turn to try a problem similar to the one that I've just explained to you. So you need to add that to your notes. I will publish the solutions to those, but I will only publish those solutions after you've had a chance to ask questions about those in class, because it's probably better if you do have questions if you ask me those questions in class, where we can take care of those in more of a give and take format. The answers to the your turn problems are, in fact, in your textbook at the end of the section, right before the review exercises for that section take place. So if all you want to know is if you got the right final answer, then that will be in your e-textbook in my math lab, so you can check that. But again, I will post the solutions to the problems on the due date for the notes. And your notes, once again, are judged primarily for completeness, not necessarily correctness. But I know that you will want to check those your turn problems, because you'll want to know if you got those right. Quick word about Chapter 11 as opposed to Chapter 12. Both of these chapters are about the derivative, which is actually to say they're about the slope or the rate of change of functions. And that's a concept that you're probably pretty familiar with. But in Chapter 11, when we start talking about the derivative, we're going to be looking at it in kind of a different way from what you're accustomed to. Slope of a linear equation is easy to calculate because all you need is 2 points. The slope of curved functions, on the other hand, like quadratics and cubics, exponential functions, logarithmic functions, and so forth, those kind of functions also have slope or rate of change, but their rate of change, unlike a linear function, changes depending upon what point you are on the function. And so the idea behind a derivative is to allow us to calculate the slope or rate of change of a function that is not linear. Chapter 11 is going to be focused on concepts that are integral to your understanding what a derivative is and actually does. Some of the arithmetic that we're going to use in Chapter 11 is fairly simple and straightforward, and some of it is going to be a little more challenging as we get into the algebraic method of calculating a derivative by something called the four-step method. That's going to come in section 11.4, I believe. But Chapter 12, I promise you, once we get these concepts down, Chapter 12 actually, for most students, is actually a little more straightforward. So if you feel a little lost or a little foggy or a little rough in Chapter 11, just be aware that it is going to be a little more challenging. It is going to take a little bit more thought. And as you go through doing your notes in all chapters in this course, one of the things that you should do is listen to the lesson, fill in your notes. If you don't understand something, or you get lost, or you get behind, stop the video and back it up if you need to, and listen again and fill in your notes. And if you still don't understand, even though you've written it down, you may want to listen to it even another time. And if you still have a question, or you're not understanding exactly what the point is, go ahead and write that down in your notes. And then be sure and ask the next day in class, because at the beginning of class I'll generally ask for questions about anything from the previous lesson, so that you'll have a chance for me to answer anything that you've got. And that way, if you have those written down, if you go ahead and you're doing your notes in Shobi, or you upload them piecemeal, and I see that you have a question, I may go ahead and just try to address that question even before class arrives. So do make those notes about things that you don't understand as you go along. So let's begin by talking about Section 11.1. Section 11.1 is about something called limits. And I'm sure you have a pretty intuitive idea of what a limit is. A limit in ordinary everyday terms, not a mathematical term, is, for example, let's suppose you were going to train for a marathon. And you're not a marathon runner. I certainly am not. So I might start out by trying to run every day, and I might see how long it takes me to run a given distance. And maybe the first day for me to run a mile takes probably 10 or 15 minutes actually for me. Maybe for you a lot less time than that, but the first time I do it, I'm going to be pretty slow. But as I train within a week or two, then my time is going to go maybe from 20 minutes to 15 minutes to 12 minutes down to 7 minutes and 6 minutes and so forth. Eventually, though, no matter how long I train, no matter how long anyone trains, their time to run a given distance is going to reach what is called a limit, because you're only going to be able to reduce your time to perform that task so much before you can't perform that task any faster. It's sort of the same thing, if you were to think about it, as it would be stacking up wooden blocks. The first time you try to do it, you might not be able to stack it very high before the blocks toppled over, but as you practice, you would get better and better and better. But eventually, you're going to reach a limit as to how high you can stack those blocks, if nothing else, just because you have height issues, and short of climbing a very, very tall ladder, you're not going to be able to stack your blocks infinitely high. So you're going to hit, it's the idea of hitting a limit. You have reached your limit. You know, and that's sort of the same thing we're talking about here in calculus. You're reaching a limit when you're trying to get closer and closer and closer to something, and eventually you can get very close to it, but a limit is going to be what happens when you get so close to it you can't get any closer and you can't go past it. That's kind of intuitively what a limit is. Now, in our previous courses, you learned about things in algebra that you dealt with what's called a static situation, a situation at a single point in time, a single value of x. For example, some of the questions that we've considered in the past is, what was the revenue for an item when 100 items were sold? We were able to calculate that because we knew that if they sold 100 items and each individual item, say, cost $5, then the revenue when 100 items were sold was $5 times 100, or $500. And that was one answer at one given point in time. And that time pretty much was static. You know, you could change to a different time, but it wasn't fluid. Same thing for how much interest is earned in 3 years on some kind of an investment that you've made. You have a formula that you plug in the interest rate and the time in 3 years and how much you originally invested, and you can calculate what the future value of that investment was and subtract what you initially invested, and you will have the amount of interest that you earned on your investment. So hopefully that sounds familiar to you from Math 1630. What is the equilibrium price? At the very instant that the price and the that when your supply and your demand are equal, they produce the same price and the same number both supplied and demanded, you find an equilibrium price, and that is at one particular point in time. In calculus, on the other hand, we're going to be dealing with dynamic situations, situations that are changing with every passing moment in time. At what rate is the demand for a product changing? When you first create the product and not very many people know about it, then the demand is probably not going to be very high. But as people find out about it and other people see people have it the demand is probably going to increase because everybody's going to want one. But then after a while, and you could think of fidget spinners at this point, that was something that was popular last year. You know, in the beginning, not very many people had them. They were not very interesting. Nobody knew about them. But as more and more people became aware of them, then lots and lots and lots of people bought them. And the demand increased and increased and increased. But eventually, everybody had one. And at that point, some people were still buying them because, you know, you bought them for your children. You might have bought them for a gift for someone, but the product wasn't selling as fast. The demand was no longer increasing. It had reached a limit. So limit ties into this idea. How fast is a car moving after 2 hours? In the beginning, the car's moving slowly because you have to apply the gas to make it move faster and faster and faster. And then you reach a traffic light and the light's turned red, so you slow down. And then after you stop for the traffic light, you speed up again. And at 2 hours into the trip, you are going to be moving at a certain rate of speed. But that rate of speed, or that rate of change of distance over time, is going to be different for every single moment of that trip. When does the growth of a population begin to slow down? One of the kinds of curves that we're going to look at, one of the functions we'll look at in this course, is called a logistic function. And if you would imagine that you've got a deserted island that has plenty of vegetation on it, and there's no animals of any kind, then you might introduce rabbits into that island. And what's going to happen if you introduce rabbits in there is that the boy rabbits and the girl rabbits are going to do what rabbits do, and eventually they're going to be baby rabbits, and the baby rabbits are going to grow up, and they're going to do what boy and girl rabbits do, and there's going to be more baby rabbits, and of course their parents are still making baby rabbits, and soon their children are going to be making baby rabbits, and after a while the island is going to be covered with baby rabbits. And that's not going to keep increasing. That population of rabbits cannot keep increasing forever. And the reason that it can't keep increasing forever is because eventually they're going to run out of food and the rabbits are going to start dying off. So that's what we call a logistic curve, where it starts out, the rate of growth is slow and steady, but slow. And then at some point, because rabbits are having more rabbits, then it increases very, very, very quickly. But then the rabbits start starving, and so the population levels off, and it reaches an equilibrium point with the amount of food that's available on the island. So those are some ideas that we can deal with in calculus. The key idea underlining calculus is that we're going to be dealing with rates of change, and we're going to be studying the concept of limit quite a bit in this course, so that's where we're going to begin. So our first problem to consider says, suppose that we have a function, f of x equals x squared. Now you're probably fairly familiar with that function. F of x equals x squared is a parabola. It has its vertex at the origin, and it's a curve. It's not a straight line. So the first problem we're going to consider here is what happens to f of x as x gets to be a number that's very close to, but not equal to 2. We want to know what the limit of that function is as x approaches 2. That's the way we'll say it in calculus. So one way that we can investigate that limit is to choose numbers that are increasingly closer to 2. And at this point, you probably want to get your calculator and work along with me here, because we're going to fill in this table. And we're going to begin by choosing a number that's close to 2, but it's not 2. And the first number that we'll choose is 1.9. So if you'll enter into your calculator the number 1.9 and square it, then you'll see that you get 3.61. Now, we can move a little closer. In fact, we can move a lot closer. We could choose the number, instead of being 1.9, to be 1.99. And if you choose it to be 1.99, which is closer to 2, then the answer that you get is 3.9601. Now, if we move even closer, then we can take the number 1.999, that's 1 and 999 thousandths, that's very close to 2. And when we square that number, we get 3.996001. And so what you see happening here, and what you may suspect is happening, is that we're getting closer and closer to the number 4. And just to, again, prove the point, we're going to let x be 1.9999. And so if you take 1.9999 squared and use your calculator to do the arithmetic, what you're actually going to get is going to be 3.999 6 0 0 0 0 1. And that is indeed very, very, very close to 4. So the way that we say this in calculus is that the limit of f of x, which is x squared, as x approaches 2 from the left, because we're starting at less than 2 and approaching 2, we say that the limit as x approaches 2 from the left is 4. And that's what we're saying here. The limit as x approaches 2 from the left for this function is 4. Now, similarly, we can approach from the right. We could start out at 2.1. 2.1 is also very, very, very close to 2. It's only 2 1/10. So if you square 2.1, 2.1 times 2.1 is 4.41. Now, if we were to move closer, say to maybe 2 1/100th, that's much closer to 2. And if we square 2.01, 2 1/100th, we get 4.0401. Which is indeed closer to 4. And if we were to move even closer to 2.001, 2 1/1000th, if we square 2.001, the result is going to be 4.00040001. And indeed, that is much, much closer to 4. And then again, just one more time, if we let it approach even closer to 2.0001, 2 1/10,000th, and we square that, the result is 4.0004000. Excuse me, I put in one too many zeros on the previous one. Let me fix that. This should have been 4.001. Didn't count my zeros very well. And this one, 2.001 gives us 4.00. Start back at the beginning. 2.01 gives us 4.0401. And 2.001 gives us 4.0040001. And that is a 4. And if you take 2.0001, which is 2 and 1/10,000th, the result is 4.0004001, which is indeed very, very, very close to 4, just as 3.9960001 is also very, very close to 4. And so we say that as x approaches 2 from the right, the limit of f of x equals x squared is also 4. I would suggest when you are doing this that you use your calculator to do these calculations. And if you did the refresher, the skills refresher that I gave out in class and that's listed in Shobi, you should know how to put that into your calculator to make your work much, much easier for this problem. So in conclusion, what happens to f of x equals x squared when x is a number very, very, very close but not equal to 2? Well, what happens is f of x equals x squared. If you let x approach 2, the limit becomes 4. Now, at this point, you're probably saying, well, why didn't you just plug in 2? You knew what it was at 2. 2 squared is 4. Yes, we do know that, but we're trying to develop the idea of what happens when something gets close to a fence that we're trying to approach. So you can think of 2 as being a fence. You can approach the fence, and you can approach it from either side, but you don't want to touch the fence. Think of it, if you've ever been on a farm and you know about an electric fence, think about 2 being the electric fence. You don't want to touch it. You just want to get close. And you can figure out what's going to happen if you get close to 2. But you can't actually have it be 2. And some more problems, we're going to see that we're going to be able to approach a number. We're not going to actually be able to let x be that number, because we'll have a problem where maybe x isn't allowed to be that number. So let's move on to the next one. And we're going to still be talking about the same problem. This is a graphical interpretation of what happens. We've investigated it numerically. Now we're going to investigate it graphically. So what we see is that if you follow the graph and you let x go, let's say from 1 to 2, what you notice happening here is I'm approaching 2 as the value of the function as I approach 2 on the x-axis, the value of the function approaches 4. And the same thing happens from the right-hand side. If I try to come at x equals 2 from the right-hand side, then what happens on the function is that my function value gets closer and closer and closer once again to 4. And so what we say in this case is that the limit as x approaches 2 from the positive side, that's the way we write it, is equal to 4. And we also say the limit as x approaches 2 from the left, which is the negative side, numbers below 2, that limit is also equal to 4. So we call this one the left-hand limit, and we call this one the right limit. I'm sorry, I said that backwards. Let me try again. This one is called the right limit because you're approaching from the right, from the positive side. This one is called the left limit because you're approaching from the left. And one of the things that we're going to learn is because the two-sided limit, the right limit and the left limit both equal 4, what we're going to say later on is that the limit does exist and that the limit as x approaches 2 of f of x is equal to 4. And that's why we say the limit is 4. And somehow I had way too many slides. Now, this is your turn. What I want you to do is I want you to find the limit as x approaches 1 of x squared plus 2, and do that by building this table in your notes. So I want you to pause the video for a minute, and I want you to get your calculator, and I'm going to give you a little instruction on this one to make sure that you're doing what I expect you to. On this one, what I want you to do is I want you to go to your Y1 on your calculator, and I want you to enter in x squared plus 2 with or without parentheses. You don't have to have the parentheses, but enter that in at Y1. Then I want you to press second window, which is going to take you to table setup. And on table setup, I want you to go down to where it says independent. And rather than saying auto, I want you to put the cursor on ask. And then from there, I want you to press second and graph, which will take you to a table in your calculator where you're putting in X, and there will be a heading on the next column called Y1. And what I want you to do is I want you to enter in the numbers getting closer and closer to 1. So a number that's a little less than 1 would be 0.9. And then go 0.99 and 0.999 and so forth until you get very close to 1. Then, from the other side, a number that's very close to 1 would be 1.1. And then 1.01 and 1.001 and 1.0001, and see what you get close to. And then at the end, you will write the limit as X approaches 1 from the left equals, and the limit as X approaches 1 from the right equals. And if those two numbers are the same, then you will know that the limit as X approaches 1 of X squared plus 2 is equal to whatever number it is that you get. So pause the video now and you try that problem. Now at this point you've come back to the video, and I want you to verify the limit you got in the last problem was what you got by actually graphing y1 equals x squared plus 2. And in this case, I'm giving you a suggestion for how to set up your window. Your x values need to go from -10 to +10, and your y values need to go from -10 to +20. And you can increment those using either X scale or Y scale. You just want to let those be 1 because you can see that many tick marks. And sketch the graph and verify by showing me on the graph what the limit is. So again, pause the video and do this part of your notes. So once we've done that first example together and you've done a second example on your own, let's try to recap what we've learned. And what we're doing here is we're giving the definition of the limit of a function. So if we have a function called f of x, or just f, and if we have two numbers, lowercase a and capital L, that are real numbers, meaning that they're not imaginary, they're numbers you can actually see on a number line, you can plot on a graph. If, number one, as x takes values closer and closer, but not equal to the number a. on both sides of A, meaning from the negative side of A and the positive side of A. As x gets closer and closer to A on both sides, the corresponding values of f of x will get closer and closer and perhaps equal to some limit that we're going to call L. And the second part of that says that the value of f of x can be made as close to L as we want to by making the values of x get close enough to A. For example, if A is 3, then we might go from 2.9 to 2.99 to 2.999 to 2.9999 to 2.99999 and even closer. And if we get close enough to 3 from either side, 3.1, 3.01, 3.001, 3.0001, 3.00001, closer and closer to 3, then we should get closer and closer to the value of f of x, which is the limit at that number A. And if both of those things happen, then what we say is that the limit as x approaches A of the function is equal to L. That is the mathematical and the calculus definition of a limit. The definition of a limit describes what happens to f of x when x is near. And again, this is the main thing. It's close to, but it is not equal to the value of A. It's not actually affected by how f of A is defined or even whether f of A is defined. F of A doesn't even have to be defined for us to be able to find that limit. And the definition implies that the function values cannot approach two different numbers. So if a limit exists, then that limit has to be unique. The left-hand limit cannot be equal to a different value from the right-hand limit, or we will say that the limit doesn't exist. So now we'll investigate by finding the limit as x approaches 2 is of g of x, where g of x is the expression x cubed minus 2x squared divided by x minus 2. And the thing that we're going to pay careful attention to here is that in actual point of fact, x cannot be 2 in this expression. Because the denominator is x minus 2, we cannot allow x to be equal to 2. That's not allowed. Now, we can find the limit graphically. We can find the limit algebraically. We can find the limit using a table. You've seen all three methods. Finding the limit with the table isn't going to be terribly difficult. We just build a table and we let x go from 1.9 to 1.99 to 1.999 and then choose x to be 1.9999, and we can also choose x to be 2.1, 2.01, 2.001, 2.00001, and even closer if you want to. And what you're going to find out using the table is that the limit is actually 4. And quite similarly, and point out to you that if you graph that function on your calculator, chances are it's not going to show you that hole at x equals 2 unless you have a very, very specific window. If you'll check in your textbook, however, on page 569, there is a picture of the graph there, and it shows you that there is a hole in the graph of f of x where x is equal to 2. Since it's easier to see on the graphing calculator, let's just look at that. If we built the table of values on the calculator, we would go to y1, and we would enter in the function, which is in parentheses 3x to the third power minus 2x squared. Close the parentheses, divided by x minus 2, also in parentheses. And then with your table set up, as I explained before, you'll go back to second graph, and it'll take you to a table that looks like this. And when you enter in your values in the table, you will go from 1.9 and see that the value is 3.61. And then you'll enter in 1.99 and see that the value is 3.9601. And then if you enter the value 1.999, you'll see that the outcome is 3.996. And if you enter the value 1.9999, you'll get 3.9996. But I also want you to enter in the value 1.99999, one decimal followed by 5 nines. Now what's going to happen as soon as you hit enter is, even though you've entered in this 1.99999, your calculator is going to call that 2. And the reason that's going to happen is because the most number of digits that it can show you are 5 digits and 1 decimal. And of course 5 digits and 1 decimal, what we have here is 6 digits and 1 decimal, and it can't show you all of those in the x column. So when it shows you the result in the x column, it's just going to go ahead and say that that's 2. We both know that 2 is not actually 1.99999. But your calculator can't show you that, and so it tells you it's 2. And when you hit enter, not only will it tell you that, it will tell you that the outcome is 4. But the fact of the matter is, it's not really 4. The y value, when x is equal to 1.9999, and 1 followed by 5 nines, is actually going to be 3.99996. And that's actually what it'll show if you put your cursor on the 4, but if you look in the table, it will say that that value is 4. Similarly, when you start at 2.1, your calculator is going to say that the answer is 4.41. And when you add a 0 between the decimal and the 1 and put in 2.01, it's going to tell you the answer is 4.0401. And when you add another 0, 2.001, the value of the expression is 4.004. And if you enter that x is 2.0001, then it comes back and tells you that the y value is 4.0004, getting closer and closer to 4. But if you put in 2.0001, 2 followed by 4 zeros after the decimal and then the 1, it's going to tell you that the answer is 4. Even though in actuality the answer is not 4, it's actually, and I meant for this to actually be the y value, the y value is actually 4.00004. 4, which once again you can only see 5 characters including the decimal. And here we have 1, 2, 3, 4, 5, 6 characters. And that isn't going to all show on this part. So that's the actual value that you get. Now, this last one is the most important one for you to actually use. I want you to actually put in x equals 2. I want you to type in a 2 in the x column. And notice that when you type in 2 in the x column, not 2.00001, when you type in the value 2, it gives you an error message. And that's because it knows that the actual expression is undefined if you let x be exactly 2. Even though it sort of implied that it was 4, that was because this wasn't really 2. It was 2.0001. So just be aware of that. So what this is telling you is that there was a hole in the function at x equals 2. Now I'm going to go back. Now we're going to try actually analyzing this function algebraically. And in order to make the math easier, what we're going to do is we're going to algebraically simplify g of x. So this is how we're going to simplify g of x. G of x is equal to x to the third minus 2x squared, all divided by x minus 2. We can simplify the numerator by factoring it, because it has a common factor of x squared. So if we factor out x squared, that factors to x squared minus, x squared times x minus 2. And of course that's over x minus 2. And we all know that x minus 2 and x minus 2 then are common factors. And because they're common factors then, we can say that g of x is equivalent to x squared, provided that x is not allowed to be 2. Because in this function, x can be 2, but in this function, x cannot be 2. So g of x, written this way, is equivalent to g of x written this way, as long as we make this restriction. And it's important that we make that restriction, because then I believe you would realize at this point that we've actually already done the limit as x approaches 2 to x squared. And the table that we looked at just a minute ago actually matches the table that you took earlier in your notes. So this would have been an easier table to make, and that would have been an easier graph to make. And then once again on your calculator, just to verify this, I want you to go to your y equals menu. And I want you to keep that function in there. That's the function that should be in there, as it says right here. And I want you, after you've entered that function, I want you to go to the zoom button, and I want you to go down to z decimal. Z-decimal makes a special window. The window originally will go from negative 4.7 to 4.7, incremented by 1, and it will go from negative 3.1 to 3.1, incremented by 1. What I want you to do after it does that is I want you to change this negative 4.7 and put in its place a 0. And then I want you to change this negative 3.1 and put in its place a 0. And then I want you to down arrow and then right arrow to the end of 3.1 and press your multiplication key and multiply 3.1 times 3. And as soon as you move your down arrow key, that will actually change then to 9.3. So this window that we're looking at down here actually goes from 0 to 4.7. And this is x equals 1, 2, 3, 4. And this is 4.7. And it goes from 0 to 9.3. And this is actually 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you graph it, what I want you to do is I don't want you to have a connected graph. I want you, next after you've done this, I want you to press your mode key. M-O-D-E, your mode key. That's not one of the keys across the top. It's on the second row. And on the mode key, I want you to down arrow on that menu and change where it's got connected highlighted. I want you to change that to dot. Connected means it'll try to connect up every pixel. Dot means that it will only plot individual pixels on your screen, which means if there's a gap, it'll show it to you. And then I want you to hit graph. So when you hit graph, this is what you're going to see. And what you should notice is right here, there's actually what appears to be a hole in that function. And that hole is where x is equal to 2. And notice that even though the y value is close from either side to 4, that when you get to that actual space, there is a hole in the function. And in fact, if you hit second and trace, on your calculator and choose value, when you get to this screen, just type the number 2 and hit enter. And when you type the number 2 and hit enter, you should see this screen. Including that hole there in the middle. Now you're probably sitting there wondering, okay, this is all really well and good, but what's the point here? Okay, so at this point, you have another problem. It's your turn to try this problem. First, I want you to find the limit as x approaches 2 of x squared minus 4 divided by the quantity x minus 2 and complete it by completing the table. Then I'm going to ask you to find the limit algebraically by simplifying that function to find an equivalent function for x squared minus 4 divided by the quantity x minus 2. And please, please, please don't forget to include the restriction for the whole, because otherwise the function is not equivalent. And then lastly, I want you to use your graphing calculator, and I want you to find the limit by sketching the graph that shows the limit. And once again, be sure that you show on the graph where the hole is. Be sure and show that hole just as a little tiny circle. So this is your turn for your second example. So pause and come back, and then we'll continue. So in summary, what we have found so far is that you can find a limit in 3 different ways. First of all, you can find a limit algebraically. And to find a limit algebraically, you're going to simplify the function. And usually the simplification is we're going to simplify by factoring. And canceling common factors. Just remember, don't forget the whole. We can also simplify by drawing a graph, either drawn by hand or with the graphing calculator. And then the third method is by using a table, once again, either written out by hand or with a graphing calculator. And in every case, the preferred method, even though you're going to transfer it to a piece of paper, I want you to use your graphing calculator to make the tables and the graphs, because it'll be easier for you that way. We're not going to spend a lot of time doing things by hand that technology can do for us. So here we have another function. Determine the limit as x approaches 2 of the function h of x, and h of x is actually a piecewise function, although it's a piecewise function that looks really similar to the very first function we investigated, which was f of x equals x squared. But what we have here is we have a limitation that if x is equal to 2, that the value is 1, because 1 squared would be 1, but not 2 squared. So we're actually changing the definition of h of x for the value x equals 2. We're adding the restriction that when x gets to be 2, the value of the function is actually 1. Other than that, if it's anything but 2, then it's whatever the number is squared. And once again, this is called a piecewise function, because its domain has been chopped up into pieces when it is 2 and when it isn't 2. So the first thing that we're going to do is we're going to go back actually to the same exact table of values that we made on the calculator much earlier. And you can go back and copy from your notes, because that's kind of what I'm going to do. So we're going to go to the graphing calculator, and at y1, we're going to type in x squared, but we're going to type it in using what's called piecewise function notation. So y1 is going to be x squared, put that in parentheses, and then parentheses after that, you're going to put in the value x, the variable x, and then we're going to need a does not equal sign. And the way that you're going to get that does not equal sign is you're going to hit your second button, and you hit your math button, and that takes you to what's called the test menu. And on the test menu, you have an option of is not equal to. And that is not equal to is option number 2. So if you hit second math, which takes you to the test menu, and then just press number 2, it will put in your not equal to sign here. And then, of course, your value is going to be 2. And then you're going to put an addition sign. And it's important that you enter this function in exactly this way, because this is how to enter a piecewise function. And then you're going to enter the number 1, again, in parentheses. And then after that, in parentheses, you're going to put in x equals 2. So this is the rule for when x doesn't equal 2. And this is the rule for when x does equal 2. And again, you can get that equal sign by hitting second math, which is the test menu. And the equal sign is the very first option on that menu, 1. So you just hit the number 1, and when you hit the number 1, that's what will give you your equal sign. So at that point, you have entered your function. And if you remember the graphing window that we were on earlier, your graph should be still not in connected mode. It should be in dot mode. So be sure that you leave it in dot mode and leave it on the window that I had you set it on initially. And to start with, we're going to find the table. And the table that we're going to build, and I'll put it in more like what we would put it in on the calculator. We're going So at this point, we're going to build the table, and I'm actually going to put it in more like what you're going to see the table on the calculator now, rather than the one all the way across the page. So your calculator screen, you'll have an X at the top of the page, and then you'll have Y1. And since we're trying to find the limit as X approaches 2, we're going to start with a number that's less than 2, such as, for example, 1.9. And we're going to get that it's 3.61. And then we'll try 1.99. And when we press enter, the calculator says that that is going to be, since it's following the rule x squared, because it's not equal to 2, that's going to be 3.96. 0.1. So then we'll try 1.999, which again is closer to 2, but not equal to 2, so we'll use the x squared rule, and we will get 3.996, and then again 1.9999, and that will give us 3.9996. But if we enter the number 2, the answer it's going to give us is 1. So that we can see as x approaches 2, what happens is that y approaches 4. But if x equals 2, then y equals 1. So the limit as x approaches 2 from the left equals 4. And then similarly, if we try to approach x from the right, or approach 2 from the right, which means we're going to start at x equals 2.1, and then go to 2.01, and 2.001, and 2.0001. This is what's going to happen. When we plug in 2.1, and I'm doing this on the calculator, assuming you're doing the same, then we get 4.41 for y1. And if we let x be 2.01, it says that y is 4.0401. And if we let x be 2.001, then y is 4.004. And if we let x be 2.0001, it tells us that y is 4.0004. And again, you could keep adding more zeros, but if you let x be 2, once again, just as before, it says y is equal to 1. So we're approaching 2. This time from the positive side. And we see that the limit as x approaches 2 from the positive side does seem to be 4, just as it was from the negative side. And yet, f of 2 does not equal 4. F of 2 equals 1. So we have a right-hand limit and a left-hand limit, but those two limits are not the same. But keep in mind, we're only looking at the limit. Okay, we're looking at the limit as x approaches 2, not where it is equal to 2. So it doesn't matter about this. It's only approaching. It isn't equaling. So just remember that that can happen. So again, I'm going to give you one for you to try. And it's a simple linear function, 2x minus 1, as long as x is not equal to 3. But if x is equal to 3, then the value of y is actually, or the value of f of 3 is actually 1. So there's your term. And you should pause the video now, and you should create your table of values, investigate your graph, and see if you get the answer that's going to be shown at the end of the section. And the end of that section is on page, trying to find it for you so I can give you the exact page you'll find the answers to the U-triads. So the answers to the U-triads for this section is in your e-text on page 584. So that's just an FYI. Here we have example 4. So here we have our next example, example 4. We are to find the limit as x approaches -2 of f of x, and f of x in this case is 3x plus 2 divided by 2x plus 4. And again, we're going to begin by finding the limit using the table. So you should go to your calculator at this point and enter this function with the parentheses at y1. And be sure that you put in your parentheses. Please pay particular attention to the fact that if x equals -2, then f of -2 is going to be 3 times -2 plus 2 over 2 times -2 plus 4, which is going to be -6 plus 2 is -4 over -4 plus 4, which is 0. So f of -2 is undefined. So similar to what we've done before, we're going to again make the table using your calculator, and we're going to try to approach -2. A number that's a little less than -2 is -2.1. You need to remember on your number line, sometimes it's a little hard to think about these things, that if we're talking about -2, that a number that's to the left of -2 is between -2 and -3. So it's going to be a little further from 0, so we'll start with a number like -2.1. And then we'll go to -2.01 and -2.001, and then -2.0001. before we try to plug in -2. And at -2, we're going to get the expected error message. And then we're going to also approach from the positive side of -2, which is going to put us between -2 and -1. So we're going to begin at -1.9. And then go to -1.99 and -1.999 and -1.9999. And again, at -2, we would get an error. So go ahead and do that problem on your calculator and check your numbers with me. So let's compare and see what happens. So when I let x be -2.1, I got 21.5. And when I let x be -2.01, I got 201.5. And at -2.001, I got 2001.5. And at 2002, or excuse me, at -2.00002, 2.00002, I'm sorry, I can't talk. At -2.001, I got 20,002. And then similarly, beginning with -1.9, -1.99, -1.999, and -1.9999, my numbers looked like this for Y1. At -1.9, I had -18.5. At -1.99, I had -198.5. At -1.999, I had -1999. And at -1.9999, I had -19,999. And yet again, at -2, both cases, I got an error. So we wonder what's going on here. Because we went from 21.5 to 201.5 to 2001.5 to 20,002. So as x approached negative 2 from the negative side, f of x kept getting larger and larger, and we say that it approached infinity. But that then as x approached 2 from the positive side, negative 1.9, negative 1.99, negative 1.999, negative 1.9999, before actually getting to 2, as x approached negative 2 from the positive side, f of x got more and more and more and more negative. It went further from 0 in the negative direction. So we say that it approaches negative infinity. So that doesn't look anything like what we've seen before. So what we can say is that the limit as x approaches 2 from the negative, or excuse me, negative 2 from the negative, was equal to infinity, but the limit as x approached negative 2 from the positive side was equal to negative infinity. It decreased without bound, whereas positive infinity is where we say that it increased without bound. So then we might wonder in this case, what does it look like? Well, if you actually draw the graph of 3x plus 2 divided by 2x minus 4, I'm sorry, 2x plus 4. If you remember from 1630, this is a rational function. We've seen these before. And this rational function has a vertical asymptote where 2x plus 4 is equal to 0, which happens to be where x is equal to negative 2. And it also has a horizontal asymptote and that horizontal asymptote, because the degree of the numerator is 1 and the degree of the denominator is also 1, then we look at the ratio of the coefficients to find the horizontal asymptote, and the horizontal asymptote is going to be where y is equal to 3 over 2, because the degree of the numerator and denominator are equal, so we use the coefficients of the x term. So the horizontal asymptote is where y is equal to 3 over 2. And what we've just seen from the table is that as our graph approaches x equals negative 2 from the left, or the negative sign, it's going to go up or increase without bound. So it's going to start out close to this asymptote, but it's going to increase without bound as it gets closer and closer and closer to x equals negative 2. And then As it jumps over -2, because -2 is the electric fence it can't touch in this case, then it actually is going to start out being very, very negative. But remember, it's approaching from the right, so it comes approaching it, and it goes down to become very, very negative. So it's going down to negative infinity when it approaches from the left. I'm sorry, from the right. When it approaches from the positive, it approaches negative infinity. But when x approaches -2, from the left side, then it actually approaches positive infinity. And you can see a graph of this on page 570 in your textbook. A much better graph than the one that I just sketched. And that graph actually in your textbook looks like this one. But since you have it in your calculator, I would suggest that what you do is set your window like the one that I'm showing you here. And then when you hit graph, since you should be in dot mode, not connected mode, you'll see that same sort of situation. And remembering then that you got your vertical asymptote and your horizontal asymptote, as are shown on the graph in your textbook. And this is an example of the table that I built for you on the previous page. So please do back up all the things that I'm showing you to do on here. Please do use your calculator to do all of this. That's very important. So just to summarize what we've just said about this function, since the limit as x approached -2 from the left increases without bound means that we're approaching positive infinity. And remember also that approaching from the left means that we are approaching from the negative side. The way that you need to learn the difference is that if we're at 0, numbers to the left of 0 are negative. Numbers to the right of 0 are positive. So when you approach from the right, you're approaching from the positive. And when you're approaching from the left, you're approaching from the negative. Also notice that as x approaches -2 from the right, that we say it decreases without bound because it's approaching negative infinity. And once again, the fact that it's from the right means that we're approaching from the positive side. What we have to say in this case, however, is that the limit as x approaches -2 does not exist And the reason that it does not exist is because the right hand limit does not equal the left hand limit. In all the other examples up to this one that we've had, the right hand and the left hand limits were equal. But in this case, they are not equal. One approaches positive infinity, one approaches negative infinity. So the limit at x equals -2 does not exist. The limit as x approaches -2 does not exist. So now you try it. You have the function to find the limit as x approaches 0 of 2x minus 1 divided by x. So pause the video and fill in your notes with your example term. Now that you've finished your term, let's find a limit of an absolute value function that is a rational function. This is going to be really similar to the last one. So I'm not going to go through all of the tables and the approaches. We're going to work actually from a graph. So in this case, I want you to go to your calculator and I want you to enter in y1 equals the absolute value of x divided by x itself. And keep in mind that what happens is that the absolute value of x means that if x is a negative number, the absolute value is a positive number. And that if x is a positive number, the absolute value is also a positive number. And that the value of x is always going to match whatever the sign of x is here. So if x is positive, then what you're going to have is you're going to have a positive number divided by a positive number, which is going to turn out to be a positive number. And since that number is going to be the same in both cases, let's say it's 1, then the absolute value of 1 over 1 is going to turn out to be 1. So this expression is always going to be equal to 1. As long as x is positive. But if x is negative, on the other hand, well, the absolute value of a negative number is positive, but x itself is negative, and a positive over a negative is always going to equal a negative result. And since the numbers themselves, once again, are going to be the same, for example, -1, if you take the absolute value of -1, that's 1, divided by -1, your answer is negative. So this expression, the absolute value of x divided by x, will always equal -1 if x is a negative number. So that's why when you look at this graph, notice that this is at x. For any number, the value of y is going to be +1 as long as all those numbers are positive. But it's going to be -1 for any number that is negative. However, at x equals 0, if x equals 0, then the absolute value of 0 divided by 0 is simply 0 over 0. And 0 is the only number that, when you place it over itself, it does not equal 1. It is undefined. Okay? So f of 0 is undefined. And what you'll see me say in shorthand here a great many times is f of 0 does not exist, DNE. That means it's undefined. So let's talk about the limits and look at it strictly from the graphic standpoint here. The limit of f of x with this being f of x, as x approaches 0 from the negative side, is negative 1. But the limit of f of x, and again, f of x is this function up here, as x approaches 0 from the positive side, which is this side, approaching this direction, is going to be positive 1. So remember, you're approaching from the positive side. And in this case, right here, you're approaching from the negative side. But at x equals 0, the function does not exist. It's undefined. So in this case, the limit of this function does not exist. Now, there are some other rules for finding limits of functions, and they give a whole list of them in the textbook, but this is really much easier if I just show you some examples about how this works. What we want to find here, and this is, I've got it down as a you try it, but I'm going to actually work this for you. If you've got two functions, one of those two functions is f of x equals 3, and the limit as x approaches 2 of that function is 3. We don't know the name of the function, we don't know the equation of the function, but we know the limit as that function's x value approaches 2 is 3. And by the same token, we know we have another function, g of x, which is different. And g of x, if you let x approach 2, its limit is 4. If you need to find the limit as x approaches 2 of the sum of these two functions added together and then squared, this is a substitution problem. All you're going to do is substitute. And then perform the operations. Okay? So this is the way this works. First of all, you can add up the limits. You can break this up. So what we're going to do first is we're going to take the limit as x approaches 2 of f of x, and we're going to add it to the limit as x approaches 2 of g of x, and we're going to add those two limits together, and we're going to square them. So the limit of f of x as x approaches 2, we have already been told is 3. And the limit of g of x as x approaches 2, we've already been told is 4. So that means when we add those together, we get 7. And since we want to square those two, we're going to square 7, and it turns out that the limit is 49, without even knowing what the functions are. So even though I had this listed as a you try it, this is not really a you try it. This is another example for you to try, just to get you into the idea of how you do where you've got different functions added together or added together and squared. You just simply, if you know what the limits are, substitute the limits in, and you're good to go. So just in summary, one of the things we want to talk about is the existence of limits. And the existence of limits basically says that the limit as x approaches a may not exist. All limits do not exist. One of the reasons that it may not exist is that if f of x becomes infinitely large in magnitude, or is positive or negative, in other words, if it just increases without bound, it approaches positive infinity or approaches negative infinity. As x approaches that number a from either side, then we say that the limit as x approaches a is equal to infinity, or it's equal to negative infinity. But in either case, that limit does not exist, because infinity is not a number, therefore there is not a limit. All we can say is that it increases or decreases without bound. If f of x becomes infinitely large in magnitude, which means positive, as x approaches a from one side, and infinitely large in magnitude, but negative as x approaches a from the other side, and just a quick sketch of what that looks like so that you'll remember. Regardless of what x, if it becomes infinitely large as x approaches a from one side, and try to imagine that's an a. My writing is not great with this. And if it becomes, as you approach from the other side, and it approaches a very, very negative number, then what that means is that the limit as x approaches a does not exist. And then the last one says that if you have the limit of some function as x approaches a from the negative is equal to one number, and the limit as x approaches a from the positive side equals a different number. If those two numbers are not the same, then the limit as x approaches that number does not exist. And that will come into play a little later on when we talk about limits and continuity. So in this particular picture, we're going to talk a little bit about what happens when limits exist and when they don't exist. So first we're going to consider when x is equal to -6. The limit does not exist as x approaches -6. And the reason that it doesn't is because when it approaches -6 from the left, it increases without bound. Whereas if it approaches -6 from the positive side, it decreases without bound. So for that reason, that limit at x equals -6 does not exist. At x equals -4, if you approach -4 from the left-hand side, we see that it approaches 2. But if you approach 4 from the right-hand side, we see that the value of the function approaches 3. And because 2 does not equal 3, that limit does not exist. However, even though f of 0 really doesn't equal 2, because we have a hole in the function there, the limit as x approaches 0 is about 3.4, because as we approach from the right, and as we approach from the negative, and we approach from the positive, in other words, we approach from the right, and we approach from the left, those limits are the same, about 3.4. Now, if you don't think it's 3.4 and you think it's 3.5, that's okay, because we're looking at a graph and it's hard to read. Our next consideration is what happens at x equals 3. Notice that f of 3 is undefined. It does not exist. But if we approach 3 from the left, we go to -infinity. And if we approach 3 from the right, we approach -infinity. But because it's -infinity, not a number, infinity is not a number, it's a place, that limit does not exist. If we're talking about x equals 4, the limit as x approaches 4 from the left is 1. And the limit as we approach 4 from the right is 1. So that means the limit as x approaches 4 of f of x is actually equal to 1, even though f of 4 is not defined. It does not exist. And then finally, talking about x equals +6, we see that it contains the point 6, 2, so f of 6 is equal to 2. And if we approach 6 from the left, the limit is equal to 2. And if we approach 6 from the right, x is equal to 2. Therefore, the limit as x approaches 6 is 2. If I were to give you advice on one thing to study in this presentation, this is a very, very, very important page to study, because you need to know when limits do and do not exist. And this is a good summary graphically of when they do and when they do not exist. Now, these are actually your rules for limits. And the example that I did as a your turn, for your turn 5, actually is what follows these limits, these limit rules. Basically, what these rules say is that if you have two functions, f of x that has a limit of capital A as x approaches little a, and g of x, which has a limit of b as x approaches little a. What we know about that is that if it's a constant that we've multiplied times f of x, then we're going to multiply the limit by that constant. If we're going to find the sum or the difference of those two functions and then find the limit as x approaches a, all we're going to do is add up or subtract the two limits. If they're a product, then we're going to take the product of those limits. And if they're a quotient, we're going to take the quotient of the limits as long as b, the limit of the denominator, is not equal to 0. And then this is some additional rules for limits. If p of x is a polynomial, and the limit as x approaches a is of p of x is equal to p of a, then that's really saying that you can substitute in a. If x is approaching a of some function and it's raised to a power, then take the limit and raise it to that power as long as that limit exists. Number 7 says, as long as x does not equal a, the limit as x approaches a will be the same as whatever f of x and g of x are. And for any real number, b raised to some function will be b raised to whatever the limit is. And similarly for the logs. These rules are not something you should remember. They will come in handy later on, and they'll provide justification in Chapter 12. But these are not as nearly as important as the prior one about knowing when limits exist. To show you how some of these examples work, suppose that you know that the limit as x approaches 2 of some function f is equal to 3. And suppose that you also know that the limit as x approaches 2 of some other function g happens to be equal to 4. What the limit rules say is that since the limit as x approaches 2 of f of x is 3, and the limit of g of x as x approaches 2 is 4, all you need to do to find the limit of their sum squared is to add the two of them together, which gives you 7, and then square it. And the answer is going to be 49. So now you try it. And I will give you a little guidance. You're going to have to find your own limits. So the first thing you're going to do, these are just hints, is you're going to find the limit as x approaches -3 of x squared minus x minus 12. And the way you can find that limit is to actually plug in x equals 3. I'm sorry, x equals -3 since it says negative. And then you're also going to find the limit as x approaches -3 of x plus 3. And again, what you're going to do is you're going to substitute in x equals -3. Pay careful attention to the fact that that limit is going to be 0. And then to complete the problem, what you're going to do is you're going to take the limit that you find here and you're going to divide it by the limit that you find here. And remember about dividing by 0. So there's your hint. Finish this one for your turn. Here's another example from me to you to help you learn how to do these. The limit as x approaches 3 of x squared minus x minus 1 would be 3 squared minus 3 minus 1, which would be 9 minus 3, which is 6, minus 1, which is 5. And the limit of the denominator is going to be this square root. Since we're approaching 3, it's going to be 3 plus 1, which is the square root of 4, which is going to be, we'll assume the positive square root, which is 2. And therefore, the limit as x approaches 3 of this quotient is going to be 5 over 2. And it would be okay to say that that's 2.5. The limit of the quotient is the quotient of the limits. Our last one is about oxygen concentration. It's an application problem. Suppose a small pond normally contains 12 units of dissolved oxygen in a fixed volume of water. Suppose also that at t equals 0, in other words, an initial time, that the quantity of organic waste is introduced into that pond, and the oxygen concentration t weeks later is going to be given by this function, f of t equals 2t squared minus 15t plus 12, divided by the quantity t squared plus 1. As time goes on, in other words, as time approaches infinity, what will be the ultimate concentration of the oxygen? Will it ever return to its initial value, which was 12 units? The first thing I want you to do is I want you to go to your graphing calculator and I want you to enter that function into y1 to make calculations easier. And remember, when you enter this function in, you need parentheses around your numerator and parentheses around your denominator. Take notice of the fact that this function will always exist. There is no way, no value of t, that t squared plus 1 would ever equal 0. So that function will always exist. It doesn't have any undefined places. Just to start investigating this function, let's think about what happens when the function is 2. Now, if you've put this function in your calculator, what I want you to do is actually evaluate this using your calculator. And as long as you've put that function in y1, the way you do this is go to the home screen. That's the screen where you do all your arithmetic. Or make use of your table, whichever one works for you. The table actually will work real well here. Actually, it's not second table, it's second graph. Which will take you to your table. And we'll be using t in place of x. And go ahead and start out at t equals 0. And I think you're going to see at t equals 0, what you're going to get is 12, which is what the problem says it is going to be. And that's because if you substitute in t equals 0, then 12 times 0 squared minus 15 times 0 plus 12 is 12 over 0 squared plus 1 is 1, and 12 over 1 is, of course, 1. At the end of 2 weeks, however, if you evaluate that function at t equals 2, that turns out to be 30 over 5, which is equal to 6, which means the quantity of dissolved oxygen has dropped to half because of that organic waste. Now, if you wait 2 more weeks until it's been 4 weeks and you substitute in 4, 12 times 4 squared minus 15 times 4 plus 12 over 4 squared plus 1, that turns out to be about 8.5. So what happens is initially the volume of oxygen that's dissolved drops drastically, but then after a couple of weeks it starts to come up. Now we want to let t approach infinity, actually, to see what happens. So in order to do that, we're going to substitute in first 10. And at 10, we see the oxygen has changed to 10.515 units of dissolved oxygen. So it's gotten higher. It's getting better. But if we wait 100 weeks and substitute 100 in for t, what we find is that it's gotten up to 11.85. Still not 12, but closer. So we'll continue the table. And instead of going just 100 weeks, we'll go 1,000 weeks. Now take into account 1,000 weeks is almost 3 years. Okay? And at the end of almost 3 years, we have 11.985. So the oxygen has come up to 11.985. If we go 10,000 weeks, which means T equals 10,000, then F of 10,000, 12 times 10,000 squared minus 15 times 10,000 plus 12, divided by the quantity 10,000 squared plus 1, we're up to 11.9985. But take into account, how long is 10,000 weeks? 10,000 weeks, since there's 52 weeks in a year, is 192 years. And if we let time go to 100,000 weeks, that's 19,023 years, or 1,923 years, almost 2,000 years. This oxygen has only risen to 11.9985. And the fact of the matter is, I don't care how large you let X be, the amount of dissolved oxygen in that fixed volume of water in the pond is never going to return to 12 units. And the reason I bring up this problem is because it's something that you will think of in business and industry, especially considering we have probably one of the top employers of our country is of our county is the Eastman. And this is something that the Eastman has to be concerned about, because large quantities of waste dumped into water, especially water that's still and not flowing, or water that's flowing slowly, the actual amount of dissolved oxygen in that water is never going to return to the same, and the more that's dumped, the longer it takes for all that oxygen to be reconstituted, or at least close to all of it. And the larger the quantity and the slower the movement of the water, the more polluted water will be, because some of the things that get dumped into water actually multiply rather than actually let the oxygen return. So these are important concepts. So what I've shown you here is the table that we actually created, and this is a graph of that function. If you'd like to look at a graph, you want to set your window up, and what you see by setting your window up to go from 0 to 12, or even to 100, I would recommend that you actually at some point let your window go out to 100, or at least 50. What you see that happens is, from the time the waste is dumped in the initial weeks, first couple of weeks, it drops quite a bit. So there's a lot less oxygen. But then once it reaches that bottom point and starts increasing, it will slowly increase. But what happens is it increases very, very, very slowly. And regardless of how long you go, It's going to approach 12, but it's never actually going to return to 12. And this is an important concept that you need to think about, even though you don't necessarily need to substitute in a bunch of numbers for this. This is going to come up quite a bit in this course, and that's the idea of limits at infinity. As x approaches infinity, which is what we were looking at in the previous problem, if you have 1 over some quantity, and that quantity gets larger and larger and larger, x gets larger. And this is an easy one to do on your calculator. One over x is 10 raised to a power. Okay? As x gets bigger and bigger, even if that power itself is small, for example, 1 over 10 squared. 1 over 10 squared is 1 over 100. 1 over 100 squared is 1 over 10,000. 1 over 1,000 squared, oops, sorry, one too many, is 1 over 1,000,000. 1/100th is small. 1/10,000th is really small. 1/1,000,000th is extremely small. And so far we're only up to x being 1,000. What happens as x gets larger and larger and larger, x approaches infinity, is that these fractions get smaller and smaller and smaller. In other words, it approaches negative infinity. I'm sorry, not negative infinity. I misspoke. It approaches 0. There is no value of x that's large enough that you can divide it into 1 and actually make 1 disappear. So the limit as x approaches infinity of x raised to that power is going to turn out to be 0. And even if you let x be negative infinity when you're raising it to powers, these numbers in the denominator still grow, or they may even, if this was the third power, it simply makes your denominator negative. And you can see that regardless of how negative this becomes, you're still dividing it into 1, and you still can't make 1 disappear. So even if x gets smaller and smaller and smaller, then you're still approaching the value of 0. This actually performs an important thing for us, which is what we were saying about limits at infinity for 1 over x raised to any power, including 1. About trying to find limits as x approaches infinity. So for example, 12 find the value as x approaches infinity of 8x plus 6 over 3x minus 1. On the surface, it looks like that'd be pretty hard, but it actually isn't. Because the way that you approach things, and this only works when x approaches infinity, the way that you do this is the first thing you do is you find the highest power of x in the denominator, not the numerator, in the denominator. And you divide through that entire expression by that power of x. And this is perfectly legal because all you're doing is basically dividing by x over x, or multiplying by 1 over x, both in the numerator and the denominator. So this is a perfectly legal thing to do. Then what happens is that the x's cancel here and here, but they don't here. These stay. So this is where your rules for limits come into play. This is kind of like the summary of the whole chapter. So that limit becomes equivalent to the limit as x approaches infinity of 8 plus 6 over x over 3 minus 1 over x. And that's going to be equal to the limit as x approaches infinity by the rules for limits of this expression, 8 plus 6 over x, divided by the limit as x approaches infinity of 3 minus 1 over x. And then again, by the properties of limits, that becomes the limit as x approaches infinity of 8 plus the limit as x approaches infinity of 6 over x, all divided by the limit as x approaches infinity of 3 plus the limit as x approaches infinity, I'm sorry, not plus, minus. Limit of x as x approaches infinity of 1 over x. Now, the limit as x approaches infinity of 8 doesn't care what x is. 8's still 8. So it's 8. And the limit as x approaches infinity of 3 doesn't care what x is either, because it's just 3. It doesn't change. And this is where things get interesting. The limit as x approaches infinity of 6 over x, I don't care how big x gets, you can divide 6 by as large a number as you want to. 6 is not going to disappear. Okay? It is not going to disappear. It's going to get very small. but it's never going to completely disappear. It's going to get very, very close to 0. But it's not ever going to actually be 0. And by the same token, no matter how big x gets, the quantity of 1 over x just gets smaller and smaller and smaller and smaller and smaller until it gets really, really close to 0. So by the rules of limits, the limit as x approaches infinity of the ratio of 8x plus 6 and 3x minus 1 is equal to 8 plus 0, which is 8, over 3 minus 0, which is 3. So that's example 12. That concludes our entire set of examples for this course, for the end of the course. We'll do one more just to make sure you understand the concept. Here we have the limit as x approaches infinity of 3x plus 2 over 4x cubed plus minus 1. And the first thing that we're going to do is we're going to divide by the highest power of x in the denominator. And we're going to divide every single term in the expression. So that's going to be 3x over x cubed plus 2 over x cubed divided by 4x cubed over x cubed minus 1 over x cubed. So since there's one x here, this becomes 3x squared, because 1 minus 3 is negative 2, and the 2 stays in the bottom. This x cubed cancels this x cubed. So what we have now is the limit as x approaches infinity of 3 over x squared plus 2 over x cubed divided by 4 minus 1 over x cubed. And what we're going to do is we're going to take the limit as x approaches infinity of this quantity. And since x is approaching infinity, that limit is 0. And then we're going to take the limit as x approaches infinity of this quantity, which is also 0, and we're going to add them together. And so the numerator is going to turn out to be 0. Then we're going to take the limit as x approaches infinity of 4, which is going to be 4. And we're going to take the limit as x approaches infinity of 1 over x to the third, which is also 0. And so 0 plus 0 is 0, divided by 4 plus 0 is 4, which is equal to 0, because 0 divided by 4 is 0, and therefore the limit as x approaches infinity of our original expression is 0. Remember, you are dividing through, when you have this kind of problem, you divide all terms by the highest power of x, in the denominator. Okay? So one more example. First thing we'll do is convert the expression. Highest power of x in the denominator is 4x, so divide through by x. 3x squared divided by x plus 2 divided by x over 4x divided by x minus 3 divided by x. Then we're going to take the limit of every one of those as x approaches infinity. So here x is going to take out the square, and we're going to have 3x. And those x's are going to cancel, which is going to give us 4. And 2 over x is going to stay 2 over x. And 3 over x is going to stay 3 over x. And so when we take the limit as x approaches infinity of each one of those, here's what happens. As x approaches infinity for 3x, that's going to be infinity. That's going to get larger forever. But the limit as x approaches infinity for 2 over x is going to be 0. And the limit as x approaches infinity for 4, well, 4 could actually care less what x is. It's just going to stay 4. And then, of course, the limit of 3 over x as x approaches infinity is again 0. So what we wind up with as x approaches infinity is infinity plus 0, which is infinity, divided by 4 plus 0, which is 4. And since infinity just gets larger and larger and larger, dividing it by 4 doesn't make any difference to it, so it just really stays infinity. Can always get a little bigger and get divided by 4 again. So that limit is actually going to turn out to be infinity. So you have one to try now. This is your turn 8. Remember that you want to divide through by the highest power of x in the denominator. And that's going to be x squared. So you finish this one. Hit pause. And go to the next slide when you're finished. So in summary, using your rules for limits, this is how taking limits at infinity works. If your function is a quotient of 2 polynomials, p of x and q of x, so if it's a rational expression with 2 polynomials, and your limits are approaching either negative infinity or positive infinity, you divide both p of x, which is your numerator, and q of x, which is your denominator, by the highest power of x in the denominator. Always in the denominator. This is what you find for your highest power of x. Okay? Always comes from the denominator. And then using your rules for limits, which says basically as x approaches infinity, 1 over x to any power is equal to 0, and as x approaches negative infinity, 1 over x to any power is equal to 0, to find the limit from step 1. We will work some problems in class to help you understand these concepts and to practice these concepts. So when you finish your notes, be sure that you download the homework assignment for section 11.1 and bring those to class with you.